This is an exploration into how this Escher's painting relates to the notion of electric fields, as well as what some of us who's teaching physics have held to be true, namely this equation there. If the calculus isn't familiar to us, at least this is. The electric field is in the direction of delta V, delta X, where V is potential. Part of this has to do with V not being well defined in certain scenarios. So electrostatic force has, the problem is that it is a conservative force. So let's explore what that even means. Now, here, let me see if I'm getting this right. Gravitational force is conservative because here's one planet, here's another planet, or any sort of objects. We can move the object from here to here. Sure, the attractive force would have diminished by then, and we can figure out using some work equals force dot change in position to figure out how much the energy has changed, or just using our gravitational energy equation, and we would have found that either if I took that more direct path from start to finish, from here to here, or if I took the squiggly path, either way, the total energy change in the system would be the same, no matter what path I took. That is part of the definition of conservative force. Now, that's not been a strong feature of how I've been teaching physics, nor how I was taught physics, so I'm going to explore this in two more scenarios before we try to contrast it with what's going on in our in this special case or unfamiliar case rather. Let's consider Hooke's law. F equals negative k delta x, right? Okay, so here we have a rubber band that is held by two fingers, and it's kind of held taut. Our end goal is to get it very stretched out, and we're going to assume that it's not going to break for our cases right now. One way you could do that is first you could loosen that up very much, and then stretch it all the way out. Or you could do it directly. You could just go stretch it all the way out the whole time. I'm not going to debate whether or not those are the same paths or not, but this certainly is two different states, fairly taut and very, very, very taut, and then either we went directly there or first we loosened it before doing it. Two states. I don't think anyone would argue that these have different types of energy. Therefore, I would say that Hooke's law, or maybe elastic force, is conservative. Sidebar, if elastic forces actually comes down to electrostatics, but I'm actually moving it, does that mean it's time varying? That poses a problem to me. Okay, but to keep it simple, we'll say elastic force is conservative, at least in the classical sense. Here's an electric field. This should be very similar to what you just saw me do on the other side with gravitation. We have a positive charge, and let's say this is a negative charge, so there would be attraction here similar to gravitation. We see R1 is smaller than R2. Oh, sorry, you see these radial electric field lines. I could have drawn this in a different color, but oh well, here we are. This electron starts out closer and ends up farther, so now there is less potential energy, unless we're considering the fact that the potential energy would be negative, so that would be more. But it's definitely smaller magnitude energy here, and with regard to infinitely far away. And it doesn't matter if I took the more direct path or if I took the squiggly path. All that matters is how far away our object is from the source of the field. Okay. Well, now, isn't there time variance as that charge is moving? I got issues over there. But anyway, here we have our example of we're going to use flux here, or the notion of flux, where we have an increasing magnetic field in this region.